Hello everyone, my name is Anurag Raj and I have pursued my BTech from IIT Roorkee, and it has been 8 years since I have been teaching and I have produced multiple All India ranks, and the topic that we'll be dealing today is N-bromosuccinamide, that is one of the most important reagent of organic chemistry, also known as NBS or N-bromosuccinamide. Now what we'll be doing today is we'll be studying in depth about the N-bromosuccinamide and the variant and the variations it can be used in. Like, suppose, what do we know about N-bromosuccinamide is NBS usually in organic chemistry is taken for allylic or benzylic bromination, but there are other applications for NBS also, and in IIT JEE Advanced or other exams it is always asked in the other variants or the other reaction in which NBS can be used. So let's start with NBS with a great amount of energy, and I hope you all be focusing over here with more concentration. Now when I'm talking about NBS, N-bromosuccinamide, it's a major function of it is brominating reagent, and this is what it is famous for bromination of allylic and benzylic position, for bromination of allylic and benzylic position. So while studying about NBS, we will first focus about how NBS is being prepared, why only allylic and benzylic positions are being brominated, why not other position, and how it is used as a brominating agent. The other use or other function of this NBS is it is also used for electrophilic electrophilic addition reaction, and as an oxidizing agent, and in the end. Now these two, electrophilic addition and oxidizing agent, you might not have studied about these reaction in which NBS is used as electrophilic addition reaction, or in which NBS does work of oxidizing agent, and the last one is decarboxylation, decarboxylating agent. So what we'll be doing is we'll be studying about all these functions of NBS and how, in what way I can predict out that NBS will be used in NBS will be acting like what kind of agent in which reaction. So the first thing that we'll deal about NBS is its preparation. NBS is prepared from succinamide, and succinamide itself is prepared from, I hope you must be known to succinic acid. So this succinamide is prepared from succinic acid, and NBS is prepared from this succinamide. Now this is succinamide, and what we'll be doing for preparation of NBS is we'll be reacting this succinamide with bromine Br2 and in presence of light. We can do in presence of light also, and the better way to do it is in presence of an basic medium. Why I am using basic medium, why not light, I'll tell you in a bit of time. Now you see, this basic medium, why I am using is, if you look at this hydrogen, this is actually an acidic hydrogen. Why it is acidic hydrogen? If I remove this hydrogen, so the base that will be produced, conjugate base that will be produced from this succinamide is, now you see this negative charge is in resonance with this pi bond and also in resonance with this pi bond. So this is a stable kind of conjugate base which is there. So this hydrogen, when removed, produces this base, and which is a very stable base because of resonance with two pi bonds of the oxygens. Now because of this hydrogen become acidic, and the easiest way to prepare N-bromosuccinamide is in presence of OH minus, although it can be done in presence of light also. But what we'll be doing today, what will be going on with is preparing it in presence of base. So as I have told you, what we'll be doing is, the first step of the reaction is when this succinamide come in presence of base, and since this is acidic hydrogen, the base will remove this acidic hydrogen and it will come out as an water, and it will produce this succinamide anion. Now this succinamide anion, what it will do is, it will come in contact of Br. Now the electron cloud on Br, because of this negative charge, it will move away, producing delta negative charge over here and delta positive over here. Now because of this redistribution of charges, this Br, the bond will break and the electron will be taken by this Br, and the product of this reaction will be NBr plus Br minus. Now this Br minus, it will react with Na present in the solution. So this will go with Na present in the solution and it will form NaBr. Now if I look at the whole reaction in one go, now see what has happened, that this succinamide, when I treated it with Br and in presence of base, this hydrogen was acidic hydrogen, it was extracted out by this base, then the anion has been formed and the anion attacked on Br molecule, and the Br molecule broke in such a way, producing Br plus and Br minus, and in that process the N-bromosuccinamide NBS has been formed. Now this particular thing is, this is our NBS, N-bromosuccinamide, and as a byproduct of this reaction, H2O and NaBr is formed. Now since I am done with this preparation part, I hope you understand why I am taking this basic medium. In presence of light, the reaction will happen. First Br will break into free radical, and then after that the reaction will start. So the mechanism will be different, but the product will be same. And also, since the reaction in case of light produced by production of free radical, it will be slow. N-bromosuccinamide from succinamide is in presence of base. Now let's move forward and see the first kind of reaction that this N-bromosuccinamide gives. So we are moving on this application part, and on that in this application part, the first thing is NBS as a brominating reagent. Brominating agent. Now you see, for brominating, if I am trying to brominate anything, the simple way is to treat it with bromine itself. Now what is the problem when I am doing reaction with bromine, and why I have to use NBS as brominating agent? The thing is, like, let's first study what if I directly react alkene with bromine and what are the problems in it. Now if I talk about direct reaction of alkene with, let's say, bromine, now this reaction itself will happen very fast. And what is the mechanism of this reaction? So if I talk about the mechanism of this reaction, what will happen is, as this Br2 approaches, will approach this alkene, you see this alkene itself has an electron cloud up and below the plane. Now because of that electron cloud, the electron cloud of Br will be repelled away, and so it will be like this. The electron cloud of Br has been repelled away, and because of this repulsion, there will be development of delta positive on this and delta negative on this. Now again this bond will break and Br minus and this alkene will attack on this Br, forming a non-classical brominium cation. So formation of non-classical brominium cation happens. Now this is an unstable cation. As you can see, there is a three-membered ring which is always strained, and Br is having positive charge which is more electronegative than carbon. So this is highly unstable. So what will happen? This Br minus which is produced from here, it will attack on this one of the carbon, and the bond of this will break and Br will form a new bond. Now what will be after this attack of Br minus? So the Br minus that has been produced, it will attack on one of the carbon and this bond will break, leading to formation of a anti-addition product of Br. I hope you might have understood the complete mechanism. Like, let's see the complete thing in one picture. So when I'm using bromine as a brominating reagent, what happens is this alkene, when this bromine approaches this alkene, because of the repulsion from electron cloud of this alkene, the electron cloud on bromine molecule moves to one end, producing a delta positive and a delta negative charge. And because of this, the electron cloud of this alkene will attack on one of the bromine, producing a non-classical brominating cation, brominium cation. Now this non-classical brominium cation is unstable because it's a three-membered ring, and moreover the positive charge is on carbon itself. So the Br minus will attack, and the attack will be anti this time. So from the opposite side, it will be attacked by Br minus, and the anti-addition product of Br will produce. Now what is the problem with this mechanism? First thing, the Br2 itself, this Br2 itself produces a lot of brown colored fume, and it's very difficult to perform the reaction if I don't have a very good gasket or a proper instrument to contain this brown color fumes of bromine, and they are highly reactive also. So in lab, when we are doing this experiment, it is very difficult to contain this Br, first of all, and second thing is I do not have any control on reaction, because as soon as I pass Br in this olefin or alkene, what will happen? This reaction will instantaneously start, and the reaction happens so very fast that I do not have any control at the rate of the reaction or the mechanism or the amount that I want the reaction to happen. Now, overcoming this problem, NBS is used. Why NBS is used? Because NBS, when I'm using NBS as brominating agent, first of all, the reaction is very slow. So NBS produces bromine in a very slow manner. If the reaction is slow, I can control the reaction at any point of time. Now, second thing is, since this NBS is actually a white color crystalline compound, so the problem of fuming is also not there. So it's very easy to brominate or to do bromination reaction with NBS with respect to Br2. I hope you understand all this. And the thing, now let's move to how this reaction happens. Now, if I'm taking NBS, so this is NBS, and if I keep it in presence of light, now you see this compound, if I look at this compound NBS, there is delta negative charge on nitrogen and delta positive charge on bromine. Even if I keep this compound in presence of light, it will just repel, or it will restrict the breaking of bond in, as what I'm trying to say is, if I keep this particular compound in presence of light also, since there is a very good distribution of positive and negative charge, and the negative charge over here is highly more also. Why? Because you see, in this particular compound, the lone pair of nitrogen is in resonance with this oxygen, double bond of oxygen. So ultimately, when this nitrogen lone pair will go into resonance with this double bond of oxygen, somehow nitrogen will attain a little bit positive charge, and because of it, that positive charge, it will start to attract the bond pairs between nitrogen and bromine, and because of that, this bond is highly ionic bond. Now the charge, because of that, the charges over there, delta negative and delta positive, are very much, so it will oppose the breaking of bond in a homolytic manner. So the earlier mechanism in which it was shown that nitrogen will take one pair and bromine will take one pair, breaking the bond in a homolytic manner, that's not the case. The actual case is, whenever NBS is there, a little bit trace amount of HBr is also present in the solution. Now this HBr, what will happen? This bond will break, both the electron will be taken by nitrogen, producing brominium ion. This brominium ion will react with HBr. This Br plus and this succinamide anion. Now what will happen? This will attack on HBr. This will attack on HBr and it will produce succinamide. It will produce succinamide and Br2. Now this Br2, in presence of light will give two Br free radicals. Now these are the free radicals which will participate in the reaction. Now let's go back and understand one more time what is happening over here and how this NBS is acting like a brominating reagent. Now you see, NBS in itself, in presence of light, cannot break homolytically. So a traces of amount of HBr that is already present in the solution takes part in the reaction, and it first react with NBS to produce succinamide and Br2. That Br2 in presence of light will break homolytically to produce two Br free radicals. Now these Br free radicals are responsible, for bromination. Now let's take a case and try to understand how the reaction will produced, how the reaction will happen. So let's take an example. Now this particular question which I am giving you has already been asked 1, 2, 3, 4, 5, 6. This question has already been asked in JEE Advanced. Now when I keep this, when I treat with this particular compound with NBS in presence of CCl4, what will happen? Now first thing that I should understand, and you should also keep in mind before attempting any question in JEE Advanced or JEE Mains, the most important thing in organic chemistry is to look for reagent and as well as the solvent, the medium. The medium plays a very important role. So we should understand why CCl4, why not water, or why not some other thing. Now you see, first thing that we'll do is try to understand why CCl4 and not other thing, not any other medium. Why not water? Why not other thing? Why CCl4? See, the main reason for this, so what is the major thing is over here is NBS. Why it is used in CCl4? Because after reaction NBS will produce succinamide, and succinamide has a acidic hydrogen which will definitely interact with the medium or the solvent. Over here it cannot react with, or it cannot interact with CCl4 because it's a non-polar compound. So what actually happens over here is, when I'm using NBS, after reaction, the succinamide which is produced, it is insoluble in this CCl4 and it will start to float over the surface of CCl4. Now, when it starts to float over the surface of CCl4, the two things happen. Two things are beneficial in that. First, it acts as an indicator for the reaction. So, if I start to see the succinamide floating over the surface of CCl4, I get to know that the particular reaction is happening and what is the extent of the reaction that has happened. Second thing, the most important is I do not have any worry to separate the byproduct from the product. Since NBS produces succinamide as a byproduct of the reaction, which is already separated out from the mixture, because in CCl4 this particular compound is not soluble, so I do not have to worry about the separation of the two things. So because of that, CCl4 is taken. If I take water, the product will be different. We'll deal also that in case of the other thing, that is electrophilic addition reactions. So if I change the solvent, the mechanism of the reaction changes. In case of CCl4, it cannot interact with the solvent or the medium, so the reaction produces in that particular manner. Now after this NBS and CCl4, one other thing that I have to take is I have to derive the reaction in such a way that it takes that particular path only of going through free radical mechanism. So in order to do that, if I have to take a particular reaction in a particular path of free radical mechanism, as you all know, we have to do or produce certain conditions in which the reaction has no other choice but to move in case through path of free radical. Now if you already have a knowledge about this, then it's good. Else, if I keep the particular reaction in a certain condition, the condition, I remember it with the help of a mnemonics, that is helper. Helper stands for heat, electricity, light, peroxide, and radical initiator. Radical initiator like AIBN, isobutyl nitrile. So AIBN is also a kind of radical initiator which produces a radical in itself, and it initiates a particular reaction to go through one of the mechanism only and only through free radical mechanism. Now please do remember this. Whenever you see the condition where heat is given, electricity means directly passing the current or electrical arc or through electrolysis. If I'm doing electrolysis, if you remember in Colway's electrolysis method also, I'm using electricity, and the particular method, the particular mechanism goes through free radical mechanism. So if I'm using heat, electricity, light, peroxide, or any radical initiator, this particular reaction is bound to go through free radical mechanism. Now, so NBS CCl4, and let me take one of the condition AIBN. This is azo-isobutonitrile. Now, what will happen in this condition is NBS, as you remember, it will produce one of the free radical, Br free radical, and this Br free radical, it will try to attack on that particular point or on that particular on that particular site where the removal of hydrogen or production of free radical is very easy. Now let's see one by one where it can attack. Now if I take this compound and see if Br attacks over here on this hydrogen, this bond will again break in a homolytic manner, producing a free radical. producing a free radical over here on this side, or it can attack on the other hydrogens also. So let's say if the attack happens not over here, but let's say on this hydrogen. This is vinylic hydrogen on this hydrogen. What it will produce? It will again break into homolytic manner. After breakage of this bond, a vinylic free radical will be produced. Now let's say if it attacks on the third and the fourth position, there are two more positions on which it can attack. Now the third position on which it can attack is, let's say, this hydrogen over here. So it will again break into in a homolytic manner, producing this free radical. And the fourth way it can attack, the fourth hydrogen it can attack, four different kinds of hydrogen it can attack, is this hydrogen over here. Again, homolytic cleavage, and the product will be this free radical. Now let's go one by one and check which free radical will require more amount of energy and which free radical will require less amount of energy. Over here, if I see in the first case, the free radical which is formed is allylic and it is in resonance with this pi bond. So it's stable. First one is stable. The second one, it's a vinylic. If you see, this free radical is a vinylic free radical. So it's highly unstable. So it's very unlikely that this will be produced. And the third one, if I see, it's also a allylic free radical in resonance with this pi bond. But the thing between the first and the second, if I have to compare the stability, this free radical is far more stable as compared to the first one because of the hyperconjugating effect of this electron chain. So if I have to keep in this particular in the four of them in order of stability, I would say the third one will be more stable, then the first one, then the fourth one, and then the second one. So the order of stability will be third greater than first, greater than fourth, greater than second. Because second one is vinylic, it is highly unlikely to be produced, and the fourth one is just a free radical. It's not vinylic, not allylic, nothing. It's just a common free radical. While the first and the third one are allylic free radical, they are stabilized by resonance. So their formation is more favored. And again, in between the first and the third one is more stable because of this hyperconjugating effect of this electron chain. So basically the third one will form our major product. Some of the product will be formed by the first one also, but the major product will be formed from the third one. The bromine free radical will attack over here. So let me copy this and then we'll move on. So the thing is, this will form major product. So Br free radical will attack on this only, and the major product of this reaction will be Br attaching itself over here. Now this is how we perform or how we go on with any organic reactions. The first thing is what you have to look is first what is the reagent. The reagent will produce attacking reagent. Second thing, the most important is you have to look for the medium, and the third thing that you have to look for is the stability of the intermediate that are being formed. And after looking these are the 3 points, if you can find out the major product of the reaction. Now I hope this whole mechanism of the reaction, if I make it in a one slide, I hope you can understand what I have done. First of all, I know my substrate, then I have seen which agent is present. This agent will produce what attacking reagent I have deduced out from here. Because of presence of AIBN, NBS will produce Br free radical. This Br free radical will attack over here. Now it will attack on which place? I have seen it will produce 4 kind of free radicals, and among these 4 kind of intermediate, I have decided out which is my most stable intermediate, and after deciding out my most stable intermediate, I have found out my final major product. So this is how, and the reason why only allylic and benzylic, I hope you understand. Now this allylic free radical is more stable. Similarly, the benzylic free radical will be more stable because of resonance, and so because of this only, the NBS act as a brominating reagent only at allylic and benzylic position. Now let's move to other kind of reaction. The second kind of reaction that NBS show is electrophilic addition reaction. Let's suppose we are taking a particular alkene and we are just treating it with NBS. In presence of, now let's take water. Now what will this water do? Please try to understand while I am doing. Now this NBS, since I have not used any of the condition which will produce Br free radical, that means this NBS will produce, if you remember, Br plus ion. Now what is the reaction mechanism? Let's understand. This NBS will react with water. It will produce NH, Br plus and OH minus. Now this Br plus and OH minus will attack on this alkene. Now this Br plus and OH minus, Br plus will attack on this alkene. It will form again the non-classical brominium ion, and after this the OH minus that has been produced will attack on one of the carbon. On which carbon it will attack? Again, you see, when this bond will break, a positive charge will appear either on this or on this carbon. The positive charge is more stable on this carbon because the carbon chain which is attached over here is longer, and it will produce more better hyperconjugating stabilization. So the attack of the positive charge is stable over here. So when this bond will break, positive charge will come over here and the OH minus will attack. So because of that, I am attacking, I am letting this OH minus attach itself on this carbon, not on over here. I hope you understand my point. Why OH minus is attacking over there only? Why not on the other carbon? Now what will happen after this? The bromine will get attached over here and OH minus will get attached over here. Now please understand, over here the addition is also anti-kind. So anti-addition. Now if I take one more example and try to understand it in a better way, let's take an alkene or let's better take cyclohexone. Let's take cyclohexone and let's react with NBS in presence of water. Now again, I hope you must remember that NBS on water will produce Br plus and OH minus from the above. So Br minus will attack on this alkene, on this particular cyclohexone. Now let me show you how this attack will happen. Now this Br minus, where it is? Now I have drawn this in a way. So this Br minus actually is above the plane, like this. Brominium cation is like this. The attack of OH minus on this has to be from below. So after this, the product that will be formed is the cyclohexone. The Br will go up and the OH minus will come down. Now I hope you understand how this reaction is happening, how this brominium cation is forming. There is two more application of NBS as oxidizing agent. You know the oxidizing agent, when it will be acting like oxidizing agent, it will be oxidizing alcohol to aldehyde, or when it will be acting like decarboxylating agent. What are the conditions when it will act like decarboxylating agent? Decarboxylating agent. Decarboxylating agent. As an decarboxylating agent, when it only acts as decarboxylating agent in one case itself, that is when we have alpha hydroxy carboxylic acid. So the main condition is it should have alpha hydroxy carboxylic acid, and if we treat alpha hydroxy carboxylic acid, it will start to act like a decarboxylating agent. Now I hope you might have understood this particular thing or this particular reagent in depth. Please look for the condition and then decide whether it will act like a brominating reagent or an electrophilic, it will do electrophilic addition reaction, or it will act like oxidizing agent, or it will act like a decarboxylating agent. So I hope you might have understood all this concept, and please be careful about the medium. It will only decide the first two things, that is when it will act like a when it will act like a brominating agent and when it will act like a electrophilic addition reagent. So that will be all for today. Thank you so much.